80s. And in these last 30 years, there's been a number of results which are really, really interesting to learn. So I was more attracted by the idea of learning something new than really using it. But then when you actually learn something, then you put some different pair of glasses, and then you see what you are doing, and like I do it in collider physics on every day, and looks different. And that's interesting, very stimulating. So my question is what I can learn. So my approach is not, if I want to test quantum mechanics in small scale, personally, it's not what I'm interested in, or whether there are alternative theories to quantum mechanics. I personally not in this business. There are other colleagues of mine that are very keen on this, and it's very useful exercise too. But my point is really, if we can, one way or the way back, relate the way we study fundamental interactions, a collider, with quantum information tools. And maybe there is something that we can learn more on our fundamental interactions, or vice versa, why not? There is something that we learn about how this works that can influence the way that quantum information concepts and quantum computing maybe are thought of now. So what about the community? So if you usual game, you go on Spires, you look at the papers with quantum HEP pH in the title or entanglement, you try to orient. And then you see that in the last year there's been an enormous number of, a consistent number of papers trying to explore these ideas more. And then, of course, the big thing changed in November 2023, not because of our workshop here, but because LHC made the first measurement of entanglement in a TT bar final state, which is what I will discuss today. I will not discuss anything else, actually, but I'll try to give you a gist of how the story went, to make you appreciate that maybe there is something interesting there. So my personal motivation, well, I have a community pride kind of thing, right? Because when I go and talk to my colleagues in quantum mechanics, actually, I was in Pavia 10 days ago, and I said that for me, quantum mechanics is a subset of quantum field theory. So who thinks of this among you? Not, for me, quantum mechanics is the limit of quantum field theory when you go non-relativistic, right, for me. And that's what I learned in school. But I said that, and then immediately a quantum person raised his hand, and he thought, he said, for me, quantum field theory is an application of quantum mechanics. So that gives you the feeling. No, but it was serious, was not joking. So this gives you a feeling how different we think about the same physics, right? I think it's socially very interesting. I still remain with my opinion, but maybe I'm gonna change. So I told you, there is a lot of results which I would like to understand if they're useful for HEP, or vice versa, right? And the reason why, I'm hopeful that we might learn something is that after all the experiments of quantum that have been done now, they have protons, electrons, and photons, right? Because they leave our scale. And we have much more in the standard model that we know exists. We have non-abelian gauge theories. We have phenomena that our friends and colleagues and our low-end, atomic scale, they don't even dream of, right? And they, of course, can say the same of us, but okay. So we have a very different view of interactions that we work with, and I would like to know whether this is useful. And then maybe, right, there is value in this. Why not? And there is a hope at the moment, a conjecture, or just wishful thinking, that maybe applying this concept maybe help us understanding better the standard model than we know of. So that's what I mean with this uncharted standard model part. So there is a lot of standard model that we don't know very well, which we'd like to know better. And why not? If we are very ambitious, we might get also new physics in it. And the story I will tell you today is on these lines, right? Really. So I'll try to build a bit of a story, not to be too boring. And I also, I will try, since this is a school, I will try to give you a crash course in quantum information in 15 minutes. Okay, so I don't know who among you is familiar with quantum information things. Good. Well, at least two. It's not bad. But I personally, I came from my quantum mechanics course in the university was the Sakurai, basically. I don't know if this book is still used, but I mean, that's the quantum mechanics that I learned. And there was nothing about quantum information. And what I'm going to cover today is this yellow slice, and it's a very small portion, very small, of what already people are exploring in, at 360 degrees. Very interesting, which I will mention at the end, the direction that people are following. So, 10, 12 minutes of quantum information. Ready? Okay, so what I learned of quantum mechanics in school was a Schrodinger equation and the wave function, okay, basically. So wave function was sum over eigenstate, Schrodinger equation the second one. If I want to make a prediction, I sandwich an operator which gives me an observable, and this is expectation value. So this is the way that we think about pure states, right? So a pure state has a wave function. Then the small chapter in the Sakurai also talked about raw matrices, okay? So raw matrices, I was being taught, are useful when you have a statistical ensemble of quantum states, right? Where your quantum state is not really pure, but somewhat your experiment or your system has some different states in it, which are a classical ensemble, in the sense that somewhat each one of them, so the raw, now I have an operator instead of a wave function, is a statistical ensemble of wave functions, right? So you see from here that this is classical because it does not depend on the phase of each state, right? There is a e to the, so the arbitrary phase and the state cancel. So you see that there is no interference between these states. Now the Schrodinger equation becomes an operator equation on rho, the density matrix, and then you still compute averages by tracing any operator over rho, right? It's the same kind of thing, but it's a more statistical point of view. So the unitarity of probability is given by the fact that the trace is 1. And then we also know that there are two, so this formalism allows you to still describe a pure state or a generic mixed one, but just looking, you can check whether the trace of rho square is equal to 1, then the state is pure. If it's not, then the state is mixed. That's what we learn. And now we go a bit more into one aspect of it. We consider a system which is composed by two subsystems. Why? Because we're going to go into the idea of entanglement, right? In the fact that there might be a correlation between a subsystem in a composite system. So we say, so I remind a few things which are important. So in a case you have a subsystem, you may have a composite wave function for a pure state, and then you can have both separable or non-separable states for a system which is composed. So a system for which the raw matrix can be written in this way is called separable. Okay, a system for which, not a system, sorry, a two subsystem. So this property is not a property of the system, but is a property of A and B. So how I partition the system itself. So it's super important. right? So the same system, the same two system overall can be partitioned in different ways. One way they can be separable, another way can be entangled, okay? So a system which is not separable is entangled, right? So entanglement is defined by saying it's not separable, it's complementary, okay? So remember again that it depends on the division. So the typical example that is given is the hydrogen atom. You take the hydrogen atom and you look it in the system of the proton. This is entangled. If you describe it in the system of the center of mass between the electron and the proton, then it's not entangled because you write it as a separable state. Okay, so the same system can be entangled or not depending on what are the subsystems. Now, then there is a theorem which says that a pure state of a system, there are two bases exist for which it can be written in this way. So it's a kind of a diagonalization of a composite system. And in this case, right, the weights lambda of each subsystem are the same one which are in front of the total one. Okay, so if a global system is in a pure state, then you can find two orthonormal bases where the total wave function can be written in this way, and the lambda sum to 1 and they're greater than 0. So this tells you that the state of a subsystem are in general mixed states, and they have the same eigenvalues, which means they are equally impure, the two subsystems. Oops, sorry. So there are two consequences. So you can always think of a mixed state as a trace out of a subsystem in a larger one. This is called purification. So if you have a mixed state, you can complement it in a way that the total state is pure, and this is called purification. And two subsystems that partition a pure state are entangled if and only if their reduced states are mixed. So now you find, for me at least, I found finally my best result to actually give up on the pure wave functions, but I really need anyway to talk about raw density matrices, because even if I have a big system in a pure, then if it's a pure system, the subsystem will be mixed. So there is no way that I can only use pure system to describe pure wave function to describe a system which is composed by subsystem. The two things talk to each other. Okay, very good. So, for example, here you show that if you have a system, so this is a Bell state, so it's a small theorem here, which is, we are writing a small set of lectures on this, very basic. So if you have a system which is in a pure state, is a Bell state, then you look, so your Bell state is the maximal entangled state for a 2 qubit, okay? Then you look at one subsystem that's maximally mixed. So it's maximally classical in a sense. And you immediately see it by doing a simple trace over the other system. So in a Bell state, each one of them is maximally mixed. Okay, then the other thing that is useful for us today is the fact that if you take an entangled pure state between two subsystems A and B, then you can define an object which is called concurrency, right? So I told you that is the system, the two systems are maximally entangled, then each one of them is in a maximally mixed state. So you can build a quantity which is called Zallis 2 linear entropy. It doesn't matter now, but you can associate a quantity which is called concurrency that tells you that measure the level of entanglement of the two A and B among themselves by computing the trace over one of the subsystems. So the more mixed it is, okay, the more entangled is A and B. Now, so this is true for a state which is pure, the global one. If now the global one, the big one, is not pure, now that's the start to having difficulties technically. There is no way so to establish whether a system, right, composed of two subsystems is entangled or not is a complicated problem if is in a mixed state. Okay, so there is no general theorem that somewhat help us to tell whether a system composed by A and B, which is in a mixed state, is entangled or not. This is a NP problem in general. If you have two qubits, right, actually there is one criterion, which is called Perez-Orodesky criterion, which is a technical thing. You compute the transpose of the rho of a subsystem, right, and then you check if all the eigenvalue are non-negative. Then rho is separable. This is a theorem that for two qubits and one qubit and one qubit goes in both directions. So it's necessary and sufficient. But apart from this case, there is no theorem that guarantees. So there are ways of detecting whether there is entanglement, but these ways are not perfect. There might be entanglement and you're not able to detect it. There's no simple way to do it. Okay, so this is just to give you a feeling. So if you have a system, I repeat, you have a quantum system. You know it's in a mixed state. Knowing if it's entangled is difficult. That's what you have to remember. Okay, it's not a problem. Now, how this has to do with the Bell inequalities as we learned them in school? Well, I mentioned them because there is also an activity on that. So, bottom line, I didn't know really well about this, so I learned it the hard way. I tell you what I understand now. If you have a better understanding, I'm all ears. My understanding evolves with the derivative, which is rather high. So Bell inequalities have nothing to do with quantum mechanics, right? So Bell inequalities are something which you can test, right? About the fact that a theory can be local, and the usual story that is out of a light cone, and then what you do here and there is independent, right? And you only say that an observable has a degree of reality, then you make measurements which are disconnected in space-light, and then you can write this equation, let's say, you can say this bound. If you measure, so the elements of a Bell inequality are, you need two polarimeters, you need measurements which are independent, and you need a rotation of the axis, which is neither like this, not like this, but is at some angle. Okay? Then you can say something non-trivial. You're calculating the expectation value of two observables, A and B, right? Where the A and B are oriented, each one on two different axes. Now, when you do this experiment, right? When you do this derivation, you use the fact, right? You use the fact that the probabilities of two independent measurements factorize, and you easily derive the fact that this linear combination has to be smaller than 2, right? This is the derivation. I think that all of us have done that once in their life, right? You don't use anything about quantum mechanics. There's nothing to do with it, okay? And then you compare with the prediction of quantum mechanics using what quantum mechanics predict, right? And you realize you compute these expectation values following the rule of quantum mechanics, and you find that quantum mechanics violates this bound. So it doesn't satisfy this locality condition and the realism condition. The other thing that is important to understand in what I'm going to say in the following, is that when I talk about entanglement, I'm within quantum mechanics. So entanglement is a property of quantum mechanics. So I cannot talk about entanglement if I'm not in quantum mechanics. However, when I talk on Bell inequalities, I can be in any theory, and then I'm testing them or not. Is that clear for the language? Okay, so we are almost done. Now, let me only explain one more thing. So I told you that for pure state, so pure state are easy because they have this property that I can know by using this concurrency if there is entanglement or not. In fact, this is not really so. Okay. Anyway, so for pure states, saying in quantum mechanics, saying that a system is entangled, you can prove that Bell inequalities are violated. It's the same thing. Okay, so any level of entanglement to some level will violate Bell inequalities, and this is proven easily. Well, I didn't take the, so you can prove it in one page. Okay, so pure state easy, and entanglement and Bell inequalities are the same thing in quantum mechanics. However, if you have a mixed state, as I was telling you before, mixed states are difficult and are more complicated, really, to understand from the quantum mechanical point of view, because they display a grading, really, of quantum behavior, which is not all entangled. So a system can have some kind of quantum correlation which is not yet entanglement, but is not classical. And this intermediate, for example, is called discord. And also here, I mean, between a state which is Bell violating and a generic entangled state, you even have another level which is called steering. So you build observable different types which somewhat are sensitive to different level of quantum intensity of quantum correlations. Even some of them are not even, have one direction only. They don't live in two directions. But this is to make you appreciate that when we, and in general, we always have mixed states for the big system, the level of classification of how they are strongly entangled changes, right? It is a grading of them. And in particular, saying that something is Bell violating is much stronger than saying that it is entangled. Okay, so for a quantum system, which is in a mixed state, to be Bell violating, you have to have a lot of correlation in it. I mean, it has to be very much entangled, so to speak. Okay. Okay, so this is was the 10 minutes crash course on the quantum information that we need. That's all. So now what I want to tell you is the story about the TOPS and the LHC. So this is a list of papers in the last few years, right? 3 or 4 years. There are many papers, even more than this. And if I forgot some, you might complain. So now there are many other papers on X, Z, ZW, final state, tau, TW. There is an explosion of papers on understanding this. So I will not talk about anything about that. I will only talk about the top. So why the top? So I was trying to argue in lecture that LHC is a top factory. We have thousands of tops created almost any second, hundreds of tops. So the decay of the top happens in 2 steps and is a semi-weak decay. I remind everybody because the top mass is high there, so the W is real. So you pay only one price of GF in the decay, not GF squared like the muon decay. So the gamma is actually rather large, right, order of GV, and that means that the lifetime of the top is very, very short. So the top is the only quark that it lives so briefly that it doesn't realize that there is QCD around. Okay, basically. Okay, so he knows he was born from QCD and then see, right? If he remembers how he was created, but once he's created, right, it's basically a weak object because it decays so fast that the time scale of the strong interaction does not have strong interaction don't have the time to kick in. So this has a property, basically, that if you look at the effective field theory, right, of this heavy quark, you realize that there is an operator, which is the chromo operator, dimension 6 again, or dimension 5, depending on which theory you are looking at. And this operator spin flips the top. So the top can be flipped, the spin can be flipped by this operator in the heavy quark effective theory, but the scale, again, of action of this operator is much longer than analyzation time, and so the top decays even before it analyzes, so there is no way that the spin of the top is changed during its lifetime. So you produce the top with a given spin, and the guy, before it can be scrambled by strong interaction, decays. Now, so first element. Second coincidence, right? The top decay, when the top decays, it happens due to the weak interaction, and you ask Olympia if you don't know the details, because now she knows everything about how this particle follows the spin. So it turns out that due to the parity violating nature of the W, the direction of the lepton is 100% correlated with the direction of the spin of the top. It doesn't mean that it goes in the same way all the time. It means that statistically, it goes much often this way and 0% of the time the other way. Okay? On a statistical basis. But that means that this guy here, so we don't have polarimeters at NHC, right, to measure the spin on the top. Also, the top decays in the beam pipe even much before everything can happen. So there's no way we can measure the spin on the top, but we can measure the lepton. This has the, also the feature of being a lepton, charged lepton, which is the best thing we can ever measure at NHC. So we know where it goes, and by knowing where it goes, we can, on a statistical basis, tell where the top spin was pointing. So we have a polarimeter, a natural polarimeter in the decay. Okay, very good. So top is special, and now we're going to use it. Okay, so now imagine that you produce, you are in a hadron collision, you produce two tops. You are, now I put myself in the center of mass frame, so they're back to back. You have a top on one side, an anti-top on the other side. The top decays in an L plus, and the anti-top decays in L minus. Okay? So this setup, I hope it's clear that it should remind you immediately of the Bell experiment. In the Bell experiment, I orient my polarimeter as I want. In LHC is the random decay of the top that orient the polarimeter, if you want. So the lepton is like my polarimeter. So in a Bell experiment, I set the axis, and then I do the experiment. And then I don't set the axis myself. But I do what we call a random tomography. It means that it's like having two polarimeters that are changing every time, randomly, uniformly. And then by knowing how the angle was, I can still do the same Bell experiment as before. It's just that they changing randomly at every time. And this procedure we call tomography. Tomography means that by reconstructing the final state of the decay, we get information on the spin states of the two top. We do the same with the Higgs. The Higgs decay into two Q threads. The W's are Q threads. Then the W's decay, or the Z decay, and then from the angular distribution of the decay, we do the tomography on a statistical basis of the states of the spin of the two W's. Okay? Is that clear? And we call this phase tomography. I'm not describing it here in detail, but it's an essential ingredient in what we are doing, and you need to appreciate it. Okay? Because we cannot measure the top spin or the W spin directly. Okay, so imagine I'm doing that, and then at the end, what I do, I reconstruct rho. So how do I reconstruct rho? So if you do the computation in quantum field theory, you realize that each of the tops are not polarized. So it's not that out of TT bar, if you look only on one top, this top has no special orientation on the spin. They're totally random, the spin. Each one of them is totally random, one and the other, if I look one at a time. However, if I look at them together, they are correlated. And that's what I mean here, right? So this is 0, right? So this is my rho. I decompose it is a tensor, right? So I can decompose it. And what happens is that this b bar is 0, but the average value of the two spins is not 0. So this is what is called the correlation metric. If CP is conserved, Cij is real and almost diagonal in the helicity basis. I also need to find a frame. So now we go a bit on the technicalities, which I'm partially interested in. But I mean, you need to choose a frame to measure the spin. So what we do for easiness, we choose the helicity of the two tops, and then we build a system out of the helicity. Okay, you need 3 axes for each one, 3 axes for the other one, and then we compute these expectation values in each axis, in each direction. Okay, so for example, xij here, this I and j can take 3 values, kappa, r, or n. So I can compute the correlation between this one and this one, or any correlation, okay, that I want. And then I can compute them, and what I find is that they're basically, this correlation matrix is diagonal. And as we learn in school, we have a 2-qubit system, and typically we can organize them in either a singlet, which is one component, or a triplet of spin. The triplet has a j equal 1, and the singlet has j equals 0. Right? Total momentum equals 0. Now, you compute, you determine this eigenvalue. They are different from a singlet or for a triplet. And then what you see, then what you do, you compute the concurrency of your system based on rho, because I can compute it, right? Given rho, I can compute the concurrency, and I find out that basically a linear combination of this CKK, there are 4 of them, and it's enough that one of these markers is less than 1 minus 1/3 for the system to be entangled. Okay, so I have one measure, so I take all of them, I compute them, and if D is less than minus 1/3, the system is entangled. This is a mixed system in general, so the fact that there is a marker is only due to the fact that I can apply the Perez-Sorodetsky system, or I can compute the concurrency, and I can tell that if the eigenvalues are like, for example, this, so these are obviously true, right, because these are Bell state, then D, if D is less than 1/3, my mixed system is entangled. So I have one object which I compute, and it tells me automatically if the system is entangled or not. Okay, I have 4 things that I calculate. And then I can also build a marker for Bell violation out of this correlation matrix. In general, they are not the same condition because the system is mixed. So, certainly, if this is satisfied, then is entangled, but not vice versa. So, if I see Bell violation, I'm sure the system is entangled, but not the opposite is not true. And I can compute this also from the data. Okay, so this was the proof. So finally, I have two things which I can compute from data that tell me if something is entangled or even by violation. So if I look at my phase space of the tops have an angle, right, cos theta coming out, and a speed, right, and velocity for their product, and energy with which they fly away from the production point. Okay, so it so happens that if you look at the GG channel, so gluon-gluon fusion into TT bar, the pair at threshold is entangled. Red means entangled, maximal entangled at threshold at any angle, and is also maximally entangled when the two tops go at 90 degrees and very high energy. And the reason there is chirality conservation of strong interaction. The two tops at 90 degrees go in the spin is like either this way or this way. So they sum to spin 1 because they have to conserve chirality. So these points are special. This point here and this degenerate point there. And they are in Bell state. So in a singlet state at threshold, in a triplet state at high PT at 90 degrees. For QQ is not true because a QQ goes through a gluon in the S channel, and the gluon S channel is spin 1. So they are in general not necessarily entangled. It's a mixed state here. But for QQ, the argument high PT is the same. So here is really chiral conservation of QCD. The QCD is a vector-like theory. So this means that they are entangled. So both these, the sum of the two gives this plot. You have the system which is entangled here on average and up there. Okay. Then what we did and other people did a few years ago, so this is a 21. So we said, how difficult will it be to detect entanglement in TT bar? No problem, as a theorist says. No, I mean, you write a paper, you say, oh, this is easy. Then it takes 5 years, right? Obviously, because what we think is easy is not never easy. But somewhat, it's true that it was feasible. I mean, that the simple calculation gave 5 sigma right away. So entanglement is easily observable at LHC. And threshold. High PT, we found, start saying, oh, it's only 5 sigma. Well, we'll do it. Well, high PT turns out is much more difficult because you have much less events, right? Just because of that. But the threshold, we thought, and not me also, the first people who wrote this paper, Afik and Gouveia, was, the Munoz said that this was going to be happening. And then in 2023-24, Atlas and CMS both detected entanglement in TT bar by measuring D. So let me read for you these plots because it will be the center of the story. Now we are in the center. So this plot is the invariant mass of the TT bar pair, and this is on the y-axis is D. So I told you if D is smaller than minus 1/3, the system is entangled, okay, at threshold. And you see that right at threshold, the measurement is indeed showing that the system is entangled. Actually, it's even showing that it's more entangled than our best Monte Carlo's prediction here. Then came CMS. So CMS always wants to do something different from Atlas. So they put D on the x-axis. Okay. So don't be fooled. So now don't be fooled. It's the same as here, but it's a d-axis. So the separable system is here. So less than minus 1/3 is here. So the blue line is the theory prediction. This is the likelihood. And the orange line here is the experiment. And the best likelihood is minus 0.5. So, rather close to this number. And for CMS also, you notice that there are more entanglement than predicted by our best Monte Carlos. Okay? So we are all happy, Atlas and CMS gets the headlines, and we are all happy, our workshop here happens at the same time. So we are all happy that final entanglement has been detected, is predicted, and is detected. And then people ask us, so what? Right? I mean, so, okay. I mean, so, and that's the point, right? That's the when the story becomes interesting, right? So what? It's predicted by quantum field theory, even in the non-relativistic limit, and we are finding what we predicted, almost. Okay, so let me suspend this for a few moments. Let me finish the story on this part. So here, then we have, what about Bell inequalities violation? Much more difficult, because you have to go high PT, and then you have to have a very high degree of entanglement, which you reach a very high PT, much more difficult. And then we start discussing here what is really meaning of Bell inequalities in this system. Is much more tricky to define, and so I'm not digging into this right now. Okay. So now let me go back to so what, right? So the question that people with our minds would ask at this point, okay, you have a new observable. It's not really new because we did spin correlations before, but let's say that you have a marker for measuring something that before you were only generally labeling as entanglement, as correlation, but you were not really looking whether a system was entangled or not. So it's something different, something new. What do you use it for? Well, then you dream, right, that maybe there is a quantum advantage, right? Quantum advantage is one of these buzzwords. A quantum advantage in the search of new physics using entanglement. Is there? I don't know. So let's see whether, maybe there is a chance. So how do we search for new physics? We are learning in school this week. Either you go with an effective field theory, or where you study the interactions, or you look for new particles, which is the dream way, right? Where you just see a new state, which was not the standard model, story over, you go get your prize, and then we talk about what it is, right? For effective field theory is a much more difficult story. So we all know what SMEFT is, so I'm not going to describe. So SMEFT is here, right? Standard model is a sphere. We slightly deform it. We don't know which animal it is, but maybe we can start seeing something that gets us in some new physics scenario. Okay, so we all know this. I don't need to know. I don't need to explain. Then I go to this plot. I put SMEFT operators there, and I take the ratio, and I check whether this is a ratio plot, if the entanglement changes, and I see that it changes very rapidly in the regions where there was no entanglement at all, which is start to be populated here. So there is a sensitivity, both in production and in decays, which is independent somewhat of the sensitivity we are used in production. So it's potentially interesting to kill some of this flat direction that you have in these global fits of SMEFT. We haven't looked at it so much in detail, but what we have seen looks promising, okay? Not like world changing, but it's gonna add some information. There is also something which are not written here. There are some behaviors which we don't understand yet. For example, a maximally entangled region of phase space is not affected by dimension 6 operators. I don't have an explanation, and that's why what we find. I was mentioning this yesterday to my colleagues. So I don't want to dig on this more. What about BSM resonances? Well, let's make an experiment. Let's make a simple exercise. Let's take a resonance, a scalar, spin 1, and then even look at 2 stops, then decay to tops, right? If the tops come from 2 stops, the stops are scalars, right? And therefore, they don't know anything about spin. And then the top that decays you get are completely uncorrelated in spin because they went through 2 scalars. So this is where our correlation matrix is nothing, 0. There's no correlation. While if it's a scalar of a z, then you have correlation which are non-trivial. You can calculate them. They're interesting correlation. So the question we ask is a very simple one. We said, take an analysis which looks for resonance with a Breit-Wigner peak. Normal. So you take the background, you look at the Breit-Wigner peak, and you determine the sensitivity, which means if you're able to tell that there is an enhancement in the cross-section in the beam, which is larger than square root of n of the fluctuation of the background. Okay, very easy. And we compare that sensitivity with the sensitivity we get from one of these markers of entanglement. One at a time, not combined, we do the easy thing. So this is a sensitivity plot. The black lines are the invariant mass search, normal bump search. So the lower is the line, the more sensitive you are, right? Because you see that this is a plot in mass on the y on the x-axis and on coupling on the y-axis. So the lower is the coupling that you can exclude, the higher is your sensitivity. Best, low. So you look for the z prime, I look at the standard search, the sensitivity plot tells me the black line is the lowest. The markers from entanglement are all higher. I don't exclude and again some sensitivity if I combine them, but somewhat there is no clear sign of improvement here, right? Because I always win with the normal n, with the counting the events under the peak. And the same for Susie. Well, here it's somewhat obvious, right? Because I told you there is no correlation. So you would actually compare nothing with the correlation of the standard model, right? But if there is no, if you're in a region where there is no correlation with standard model, you don't gain anything. So it's not bad. So this cos phi is not bad, actually, masses. But somewhat you knew that this was not going to tell you much because there is no entanglement, right, in new physics. So you would only detect it because there is nothing with respect to the standard model. What about the scalars? Well, the story for the scalars is completely different. And the reason, you can, I mean, the result, you can show it here. So there is one marker for the pseudoscalar and one marker for the scalar, which is, you know, better alone than the peak reconstruction. And above all, in the pseudoscalar state. So why? Well, because a TT bar pair, if it has a very low momentum, right, and is produced at threshold, is in a singlet. And you will have the quantum numbers of a pseudoscalar because of QCD, right? So a state which is a TT bar is in a pseudoscalar state at threshold. We call it 1s0 or eta, if you want. So the spin correlations are a lot. Okay, so we wrote this paper in December, January. Okay, and then came these latest editions of CMS Atlas, which showed again. So we went back and said, well, that's interesting, no? There is more entanglement than what QCD predicts. Well, maybe there is something there beyond the standard model. No, because it's not very significant, but both experiments are seeing it. So you can imagine, right, that you go there and say, is there anything that could be close to threshold that would change and increase the entanglement? The answer is yes. The first answer is yes. Is if a 2x doublet model pseudoscalar is there, the entity bar, it would have increased the measurement of entanglement because that is fully entangled. Okay. So what actually everybody what was not thinking about until these two measurements came about was the fact that actually there is a somewhat uncharted standard model territory physics there, which is a toponium state. So toponium, the physics of toponium is well known since the 86, okay? So it's nothing new. But somewhat people have forgot it is itself because the top I told you the decays before even having the time to hadronize, right? So you produce a TT bar pair, they start exchanging a gluon in a color singlet, then they start seeing each other, and then one of them decays, right? So it's like a Romeo and Juliet story, right? It's a very sad story. By the time they get together, one of them dies, right? So do we still see something? Well, the answer is yes. It's actually how we will measure the top mass and FCCEE when we build it, right? This is shown in the left-hand side. So the cross-section get enhanced there, even though there is not real bound state. It's a kind of a pseudo bound state. So there is an enhancement on the cross-section due to the fact that the TT bar gets closer in phase space there in this for a while. So our friends in Japan and even in Germany were daring in 2008, 2009 to say, well, if there is this any plus and minus, there will also be a PP. And they wrote a paper, and I, in first person, 2009, said, you'll never see it, right? No way. Because look at how big is the peak. So this is the total cross-sectional threshold. Then the cross-section still rises a lot, right? So you have this little deep peak there, which is only the color singlet channel, because in a color acted, the tops get far one from another, right? It's repulsive, the octet channel. So there is no enhancement in the cross-section. And the singlet happens in 1 every 9 times, 1 every 8 times of color combination. So it's very small. Okay, in fact, the color singlet is smaller than the color octet, but the threshold, it gets a small enhancement. Then, of course, so thrilled by this, right? Groups start, we also looked and said, okay, let's build a simple model with a scalar. I added a scalar to my theory, right? Because I had no time to build a Monte Carlo with a QCD prediction. But the important point here is to notice that for the toponium, there are no free parameters. I know everything about the toponium. I don't know it very well at PP collisions. I should improve our prediction, leading order, next to leading order, and so on. But there is no free parameter. It's QCD. Okay? So you know the wave function. You know everything because it's perturbative. It's not like JPSI where you don't know the bound state, wave function of the bound state. In the toponium, you know everything. You know where it is. So it's a 2 GeV below the threshold of the pole, right? Twice the pole mass on the top. And you know the width, because the width of the toponium is twice the width of the top, because I told you that its lifetime is when one of the two decays, right? And one of the two is half of the lifetime of one of the top. Because either one can decay. So this you also know. So we build this simple model, man, graph, blah, blah, simple thing with a pseudoscalar. And then we tune the cross-section, which we could calculate, but we didn't have the strength to calculate. So we tune it 2e plus e minus result, which is known, and then n and l, and l cube accuracy, right? Super duper precise. And then we take the same model, because this is a J psi kind of state, but you can predict that the mass is the same. The hyperfine splitting is very small. So you take the same one and you put in on top of the QCD prediction, but now this is a Monte Carlo. Okay, so the orange line here dotted is my Monte Carlo, which I take and give to the experimentalist. Okay, another group did that. We didn't give it to the experimentalists, but another group did the same. Fuchs and Aguivara, one of the authors of this paper, and they gave it this extra thing, which was an add-on to the Monte Carlo, right? So you add the toponium to your Monte Carlo, no interference, nothing, just add it, and then you look at the d variable without the toponium and with the toponium, and you see that the d gets smaller, significantly smaller in this region. And then you look what happens in your simulation. CMS did it. So they ran the Monte Carlo as before. The Monte Carlo is less entangled than your data. Then you add the toponium and you go in the right direction. Okay? Is this an observation and this an evidence? No, right? Because you have to still pass some criteria to get to these keywords which are reserved. So I call it tantalizing indication of new standard model physics, but it's it's rather natural that we are seeing, right? I remind you that the normalization and the position are fixed. Okay, so by doing that, you go right in what is measured, both Atlas and CMS. This CMS Atlas is still doing it, let's say. Okay, this was my story. So now, when you ask, so what? Well, at least I have one example where this actually looked useful, because I'm sure that if people wouldn't have looked at it with these entanglement eyes, it would have taken a bit more time to realize that maybe there was something there. Okay. So there are new directions, as I mentioned, very often. So I'm almost done. So if you want to look on the archive, there are many ideas, right? If you read them, there are even very interesting and challenging ideas. One of them, which I find it extremely interesting, is whether this idea that maximization in a system of entanglement or minimization, we don't know yet really which criterion is the right one, just to tell you that it's still exploring. Jesse Thaler, MIT also, sent a paper a few months ago arguing, right, I don't know if you've seen it, that if you use a minimal entanglement principle, you can derive somewhat the structure of the CKM by studying the scattering amplitudes of quarks together. So a kind of a principle of kind of a symmetry or dynamical principle that can put conditions on the structure of the interaction. The other thing that we are looking at are higher order effects, right? We are looking at X in 4 leptos, for example, and seeing that this work by Alessandro Micini, Michele Grossi, and Giovanni Piniccioli, where they also saw that the effect of extra radiation changes the pattern of entanglement for X into 4 leptos, not very much for the top, okay, but here there are potentially large effects. So there is all kind of direction that now we are exploring. To use this observable is most of the time is just speculation. We don't know if they're going to be useful, but somewhat have some kind of feature that we didn't pay attention to before. And if you are more ambitious, then maybe you can really learn something about fundamental interaction. So this is it. These are my conclusions. I already said what I wanted to say, so I stop here, and I thank you for the attention. Yeah, yeah. So, well, I think I can. Then let's see. So, so for germanium or bothonium, right? Germanium and bothonium, the lower line state is called eta. Here is eta B, and this is eta C, and these states are singlets in spin. So we label them with the 1s0 state. So the spins are anti-aligned. There is no total angular momentum, and so no L. L is 0, and the only angular momentum is coming from the spin, which is 0 because they are anti-aligned. So you can prove, it's proven in Landau, for example, in a small exercise, that the lower lying state is a spin singlet, because if you take the non-relativistic limit, you go in the spin singlet. Okay. Then the next state, which is a 3s1. So let me do like this. A 3s1. This is the upsilon or the j psi. So this is as the numbers of a photon, the quantum numbers of the photon. So it mixes with the photon. Is a vector, right? J equal 1. And the spin now are aligned. So L is still 0, but the spins are like that. And so the total angular momentum is 1. This state is slightly higher in energy than the pseudoscalar. However, we discovered 50 years ago the J psi because, well, at least in the West Coast, because it mixes with the photon, right? So we need E plus E minus, and then a J psi, and then was a peak in the cross section. So a TT bar pair at threshold has these numbers in glue. In E plus E minus has these numbers. So if your system has a mass here, the mass of the upsilon, the mass of the eta B are different by some MeV. But for the toponium, which is a very heavy state, the splitting depends on the inverse of the mass. So the splitting is very thin. So basically, for our resolution, if you predict the mass for the 3s1, you also know the mass of the 1s0. They're very close. But in glue is a 1s0. The state is a singlet. Yeah, so there are, well, right. So that you can complicate your life as much as you want. For example, people talk about tripartite entanglement even in X to WW, because if you use a coordinate system which is not aligned in the direction of the decay of the W, you have L, you have the spin of the 2W, so you have a system which has 3 angular momentum, and these are entangled. So it's already a tripartite entangled system. Or you can do like TW, BW on one side and T on the other, or things like this. So there are first papers on that, and as far as I know, I don't know now if there's something new that we could somewhat detect there, or it's just complicating things too much, let's say. This I don't know, but there have been the first proposals already. So a composite system of three objects. Yeah. Is that? Yeah, in this basis. So yeah, okay. So at this level, right? I mean, before we were talking about entanglement, we were still talking about Cij since 20 years. It's called spin correlations, and people at Tevatron and LHC studied this very well in all possible details with no next to linear correction and so on. So I'll make the story short. So if you do production of QQ bar to TT bar, which is the leading production at Tevatron, there is actually, you can actually find a direction where the spin is exactly, the spin correlation are maximally visible and is perfectly diagonal. And this can be defined in a QQ bar system. So in a QQ bar to TT bar, you can find this angle, this basis of spin, where you have maximally spin correlation, which means that it's diagonal. Now, in glue, this is not possible because the glue has two components. As it comes from glue, so there is the zero angular, total angular, and there is spin 2. So there are two components, and the two components have not common axis. So it's still anyway a state which has no optimal direction. Okay. Still, it happens that if you choose this basis, at the end, the off-diagonal terms are small. Now, why they are small? I think it's just because of in these regions, there are Bell states. Okay, so if they are Bell state, then they fall into this diagonal thing. So when they are Bell states, they are diagonal. So if you look there, it's basically diagonal. But there is no optimal basis at the LHC. Yeah. So notice also something that I forgot to show, to underline, that there are regions, like the white region here, there is no entanglement. This system is not entangled. Okay, so there are, the TT bar are still correlated in spin, but not enough to be entangled in a mixed state. Right? So this is obviously a mixed state because entanglement doesn't correspond, right? There are regions where there is no correlation. No entanglement, sorry. There is no entanglement, but still are correlated in a non-trivial way.